Okay. So inshallah, we shall try to do as quick as possible. So we are talking about the control rectifier, and the control rectifier, you know that the control rectifiers will use thyristor as the device, right? So to turn on any thyristor, so it has to be forward biased and gate pulse has to be applied, right? So, and how to generate the gate pulse in the last class we have already discussed. Now today, we shall first see what are the practical thyristor converters. 6.2.3 from your book, if you look at this. We are still following the Ned Mohammed, third edition. Okay. Now, the next figure, if we go to that figure, there are two figures if you see here. So this part, this is from the source, your source voltage. Our source voltage is say from your single phase AC supply that is available at our room, maybe in our room. And here, this LS, that this is the source inductance. This LS is the source inductance. And here's the voltage. And we shall just like that, we have set 4 thyristors. And this LD, that is inside the load actually. So this is for your single phase breeze rectifier. And this one is the 3-phase breeze. 3-phase breeze rectifiers will have 3 legs, 1, 2, 3. And it will be 1, 3, 5. This is the way to that thing. So then this will be your 4. Then that will be we have 3, 3, 3, 6, this is your 6, and this is your 2. So this is the way we have to level our thyristors. Then we will see that 1 and 2 will be conducting, and 3 and 4 will be conducting, and 5 and 6. Here, the single phase T1 and T2 will be conducting for the positive half cycle, and T3 and T4 will be conducting. Okay, when we will discuss all these things, we will come back, inshallah. So this LS, this LS, this LS, all these LS are the source. And this is the load. This is the load current, this is the load inductance. So now let us start with the single phase converters. Here in your book, they have started with the highly inductive load, but I don't want to go directly for the highly inductive load. Let us study for the resistive load first. So here, if you look here, you have to highlight this one. So if you see the highlighted portion, that will be an idealized circuit with LS equal to 0. First, we shall not consider any source inductance, and here they mention that we shall take that ID equal to capital ID, that means highly inductive load. But before going to the highly inductive load, let us study for the resistive load. I'm going to share the whiteboard. Okay. So this is I'm drawing now for the single phase, I will start control rectifier. So these resistive load things are actually should be covered in the way I am drawing. Just look at that. That will be helpful for you to draw it in future or in exams. So that will be your source. So this is T1 and this will be your T2 and this is your T3 and this is your T4. And this is your VS. The input voltage will be your VS fine upon the T. And this is your IS. And the load side, okay, let us first start with the resistive load. And I have mentioned already. So this is say IDT. And from here to here, we shall take the instantaneous value of the output voltage. We do with respect to T. So now, this will be your input sinusoidal voltage, source voltage actually, source voltage, and we shall have apply that. We shall have to apply IZ1 and IZ2. That means this is your IZ1, this will be your IZ2, and this will be your IZ3 from the gate, and this will be your IZ4. Okay, so for the positive half cycle, also draw so for the positive half cycle, so this T1 and T2 will be forward biased. Am I correct or not?
Yes, sir.
Current will go like this. So for the resistive load, IS will be equal to, not only for the resistive load, IS will be equal to ID. If you follow the path, look here, look here, look here, look here. So IS equal to IDT, right? Sorry? Yeah, sorry, yeah, you are correct. So it has come back T1 and T2. You are correct. So this is the path the current should flow, but if unless you apply any gate pulse, we have already seen in the previous class, this is IN, so there will not be any current. You can apply any voltage, all the voltage you can apply, this voltage to your T1 and T2, but since you have not applied any gate pulse, so there will be no current. Okay, we are applying a gate pulse here. At omega T equal to alpha. So now 0 to with this range, what should be the current with your load?
0 ampere.
0 ampere, right? Because your thyristor is not conducting, it is off mode. So if I now plot the current will be 0. And if the current will be 0, the voltage will be also 0. Because GDT will be your ID plus multiplied by R. If IB equal to 0, current will be 0. Now we have applied a gate pass here, and for the thyristors are forward biased, the current should start going. And the ratio of the current should be the same as your voltage. And the PD, if you If we apply the Kirchhoff voltage, then here will be a V for your alpha to pi. Okay, this is your V2. So current is 0 here at omega t equal to pi, and also the voltage is going to negative. So what will be the switching condition of the T1 and T2 after omega t equal to pi? The condition to switch off any electronic device, power electronic device, is that it must be reverse bias as well as the current through it must be 0, and we got both condition here at omega t equal to pi. So, so the T1 and T2 will be reverse bias after omega t equal to pi. But since the voltage has reversed this direction, then your T3 and T4 will be forward bias after omega t equal to pi. But we shall not apply any gate pulse. Gate pulse will be this is your pi and this is your pi, and this will be a pi plus alpha to get the symmetry there. And then T1 and T2 will be T3 and T3 will be conductive. So between them pi to pi plus alpha. So here this is your say pi plus alpha. This point is pi plus alpha. So pi to pi plus alpha, no thyristor is conducting, right? Am I correct or not?
Yes, sir.
Okay, so after pi plus alpha, we have applied the firing pulse to T3 and T4, so it will start conducting, and just like that, we shall get the we shall get the output voltage like this, and current, the ID current, the output current ID will be like this. And again, for the next after the one complete of cycle, then again we shall apply another pulse here. That will be a twice pi plus alpha. This one is twice pi plus alpha, and then so on. This will go like this. Now, if we want to plot the IS will be IDT, as I already mentioned that. So if you alpha, so it will be like this. And for the negative half cycle, you know that if T3 and T4 will be conducting, if you follow my path, then look here, T3, T4, and T3 here. So this is also IS. So this IS reverses this direction. So we should get the mirror replica of here. So the current is continuous or discontinuous now? This is your pi, this is your pi plus alpha. So this is your IS. So current is continuous or discontinuous? The load current, source current, also the load current. For the resistor, what you look here, this is the current 0, and it will keep 0, and then. So do you know what is the definition between continuous and discontinuous? Sanjida, did you join?
Yes, sir.
So what type of current it is? Discontinuous or continuous?
Discontinuous.
Discontinuous. Because if the current falls to 0 and remains 0 for some time, it is discontinuous. So for the resistive load, we see that it is a discontinuous current. And what is the average value of IS?
0, sir.
Average value 0. So should it contain any harmonics other than the fundamental? Is it that the IS current is sinusoidal or not? Not sinusoidal. Some portion is clipped. Is it sinusoidal or non-sinusoidal? Any other person other than IUT? Non-sinusoidal. If it is non-sinusoidal and repeating, then it will contain some harmonics. So will there be any even harmonics? Are you sleeping?
No, sir. Only one harmonics.
Why?
Symmetry. X-axis.
X-axis, right? You are correct. So there will be no even harmonics. Okay. So now I'm trying to find out the average value of the output voltage. So our target is we want to make AC to DC, right? So we want to see what is our DC voltage. So VDC, sometimes people call VDO. O means there is no, say, I should say VD alpha maybe, or L equal to 0, whatever. So VD alpha maybe. Alpha means that you are applying the firing percent over T equal to alpha. So the output voltage wave shape will be this is your alpha and this is your phi, and this is your phi plus alpha and this is your twice phi, right? So how can I get the average value? We have to find out the area here and then divide it by pi because it is repeating, right? So area alpha to pi and then root 2 Vs, the equation of this curve is root 2 Vs sine of omega t, d of omega t, and we have to divide it by twice pi or pi.
So is it pi or pi minus alpha? Divide by.
Yeah. You have to take it by, say, we don't have anything, but it is repeating here, right? And
Yes.
then it is going that and it will be repeating from here. So what would be your period? Tell me. What should be the time period of this kind of thing?
Pi, sir.
Because you don't have get anything. This portion with this portion will be the same as this portion. Although my drawing is not correct, so it will be pi. So now, if you do the integration, then that will come as root 2 ds by pi, then 1 plus cosine of alpha. Okay. Now, if alpha equal to 0, if you start here, and if you are applying the firing pulse here, then if you put alpha equal to 0, then what you should get root 2 ds by pi multiplied by 2. Then what it should be? The output voltage wave shape will be like this. It is same as the diode rectifier. Am I correct or not? If alpha equal to 0. You understand it or not?
Yes, sir.
You are confused. It seems like you are confused. You are now applying the firing pulse at omega t equal to 0 to T1 and T2, and you are applying the firing pulse at omega t equal to pi to T3 and T4. This is your input voltage. This is your input voltage. You are applying the firing pulse here and here, and also you are applying firing pulse here. It is IZ1, IZ2, it is IZ3 and IZ4. Then what will be the output voltage? How it should look like?
Normal full wave.
So just like the input voltage.
Yeah.
No, not the input voltage rather than the diode rectifier. Input voltage, yes, rectified, right? And what is the average value of this one? We have already calculated
0.9 Vs.
0.9 Vs, right? So if you put here, it will come 0.9 Vs, right? I want to get the VDC should be your 0.5 Vs. Then what should be the value of alpha?
Should be 45 degree or pi by 4.
Alpha equal should be 90 degree.
90 degrees.
5, yes, 90.
So you put alpha equal to 90 degree here. So then what? Cosine 90 degree is what? Cosine 90 degree is what? 0 or
0, sir,
1?
0.
0, sir, 0. Okay, 0. Sorry, this one is 0. So You don't have to use other than 1, and then it will be 4. You understand it or not?
Yes, sir.
Oh, graduate students.
Yes, sir.
Okay. Suppose you are getting the RPM. Yes. Okay. So suppose that you are trying to operate, control the speed of a DC motor by using this thyristor control rectifier. So this is the RPM 1500 is the maximum RPM. Here it is minimum, and the motor will be rotated at 200 volt. When then the motor will be at the rated speed at 1500 RPM. Okay, do you understand what I want to say? Suppose this is your say 50. Say this is your 100 volt. So at 100 volt it should be 700, say 50 RPM. So now suppose you are applying what should be the value of the alpha? Okay, this example is not suitable here because this I was talking about the resistive load. For the resistive load, the expression will be different. Okay, let us go for the inductive load. Then we shall talk about this. Okay, inductive load. So single phase rectifier, single phase control rectifier. Highly inductive load. This topic is 6.3.1. So highly inductive load. So is it raining in your area?
Yes, sir.
Already started raining?
Yes, sir.
Here what is this? There is a sound. What is the English of that sound? Thunderstorm. Thunder. Thundering sound is coming. So the current may go off at any time. But I should be able to conduct your class because I have, but I don't know what about you. I have that mobile data. So I can use. So if current fails, so don't get panic. Try to read the class because we don't have sufficient time. Here. IS, and this is your ID constant, highly inductive load. Okay. This is this one, your T1, and this is your T2, and this is your T3, and this is your T4. So we are analyzing the same circuit. Abu Bakr, did you join? Abu Bakr, yeah, I got the assignment of Ashraful Midha and another Aminul. Okay, so now let us first draw the output connect. This is your IBT, I want to plot the output current. What should be the ratio of the output current? I want to plot it. Can you hear me? Hello? Can you hear me?
Yes,
Yes, sir. we can.
What should be the ratio of the output current?
sir. A constant value IT.
It should be parallel to the omega t axis, right? And that should be your right. So we have, our load is such that there should be always a current. So then how we shall operate our thermistors? So okay, this is, suppose I am putting this way here in the same step. This is your IG1, IG2, and this will be your IG3 and IG4. Then if it is alpha, so this one is the positive voltage, T1 and T2 should contact, and the current will be, IS current should go like this. What should be the ratio of the IS? So plot IS here. So plot IS here. And suppose okay. So IS will be, which is alpha. 0, this is alpha, so IS should be. Look here, what will be the IS? IS should be your ID, right? Capital ID. Am I correct or not?
Yes, sir.
Okay, so up to pi we don't have any problem because we are getting the positive voltage, and also we have already triggered, and T1 and T2 could be conduct. But here between your pi to, this is your pi plus alpha, although T3 and T4 are forward best, but they are not ready to conduct because we have not applied any firing pulse, right? So then, but current should be always constant. Then who will carry this current? You have not fired T3 and T4, but still the current is here. So who will carry this current? Pi to pi plus alpha. T1, T2 should be conducting, forcefully conducting. Okay. So now, so that should be your conduction period of T1 and T2. And this point is pi plus alpha. So you have applied the firing pulse to your T3 and T4, and then immediately T3 and T4 will be conducting. If T3 and T4 will be conducting, okay, so here negative to positive, T3 and T4, and IS will be negative of the previous one, and IS will be also same as your ID, but it will be negative. So that means it will go here. So now T3 and T4 will be conducting until twice pi plus alpha, because twice pi plus alpha we have applied IG1 and IG2 again. So T3 and T4 should conduct until twice pi plus alpha. So now if we look at the or apply the Kirchhoff voltage law, then after alpha, Vd must be your Vs. As long as T1 and T2 is conducting here, good, it will be like this. And then when T3 and T4 will be conducting, and that will be, of course, rectified, and we should go the again Vd must be equal to Vs, and Vs like this, and then it will follow like this. So twice pi plus alpha, is it not same to 0 to alpha?
Yes, sir.
because
sir.
it is starting of a new cycle. So it is starting of a new cycle. So we got this one, and that is your T3 and T4. So here output voltage wave shape should be like this, and during this period T3 and T4 should be conducting like this. Actually, if you go back, it will be like this. So you got my point. So now here this is the time period 0 to alpha T3 and T4, alpha to pi plus alpha, then T1 and T2, then pi plus alpha to twice pi plus alpha. This is twice pi plus alpha. So this period will be your T3 and T4. This is again T1 and T2. You got my point or not? Hello.
Yes, sir. I think we got it.
So if you read it, then it will be clear. Now the shifting of the current from T1 and T2 to T3 and T4 will be instantaneous, right? Is there any delay?
No, sir.
So there will be no computation delay. Okay, now
Sir, I have a question, sir. Here the output current is always ID. So what is the purpose of my firing of alphas? Either forcefully or naturally, the diodes are always conducting. I mean, even with different alpha, I'm not getting any control on the output current.
no. If you don't apply any firing pulse, if you don't turn on your devices, then how will you get who will supply this current?
Sir, I mean, sir, after once I turn on, there is the ID is always same, like
Yeah, it should. Yeah, it should be like this, and then you know that then you will not get the rectified wave. Your output voltage will be like this. If you don't you don't want to apply this one, firing pulse to your T3 and T4. You don't want to apply. Hello.
yes, sir. I mean, sir,
If you don't apply, then what will happen? If you don't apply, then what will happen? Tell me. So T1 and T2 will be still conducting because this is a highly inductive load and you did not give any path to flow the current. So T1 and T2 will be conducting and you will not get the rectified wave.
okay.
Okay, so our output voltage wave shape will be like this. You think you will get the answer. If you don't give the firing pulse here, then it will continue like this. And then you will get the input voltage will be your output voltage. You got my point? Our purpose of AC to DC will not be achieved.
Yes, so
This is
it's
your
the
alpha.
output
Yes.
voltage we are controlling with the diode, not the output current.
Right. Here the output voltage. Control parameter is the voltage, not the current. Current will be always constant. So, and this is your Vs, and that will be √2 Vs sine of omega t. And now this is 0. So I want to find out the average value again. So Vd alpha. So Vd alpha will be. Let me check whether they put, yes, they put Vd alpha in the book. So Vd alpha then we have to integrate it between alpha to pi plus alpha. Am I correct or not? Let us take this question and divided by 1 by pi, then √2 Vs sine of omega t, d of omega t, then √2 Vs by pi, then cosine of alpha. Now it will be like this. You got my point? Hello.
Yes, sir.
So now if you look here, if alpha equal to 0, then it will be just 0.9 Vs, right? If alpha equal to 0, if we apply the firing pulse here, it will be just like your diode rectifier. And we have started this one, if you remember, for the diode rectifier case. But if alpha equal to now 90 degree, what should be the output voltage?
0.45.
You put alpha equal to 90 degrees. So this part is equal to this part. This part is equal to this part, and this part equal. So you put alpha equal to 90 degrees here. Cosine 90 is what?
0.
0. Then you should get 0, right? Because you will have the positive part of the voltage should be equal to negative part. You understand what I say? This is your alpha, and this will be your pi plus alpha. So if you integrate over this one, if you apply alpha equal to pi by 2, so you will have the positive part. It will be exactly negative part. Then what will be average value? Hey, 0. Why you are confused? Suppose you are getting like this, okay, like this, and you are getting like this. So this portion is equal to this portion, and also this portion equal to this portion. So you will not get. And from the mathematics, it is also true. If you put alpha equal to 90 degrees, you see alpha equal to 0. Now I want to make alpha equal to more than 90 degrees. What will happen? Your voltage will be positive or negative?
Negative, sir.
Your voltage will be negative. If the voltage is negative, then output voltage ID is constant, and your voltage is negative, VD alpha, then your this PD will be negative. So then we have already told you we can operate our thyristor control rectifying the two mode of operation. This is your rectifying mode, and this is your inversion mode. Can you remember in the last class? Your voltage is negative, but the current is always positive. So you will feedback the power to the input again. You can do that thing. This is the inversion mode of operation. We shall study this thing, inshallah. Okay. So what is the, because of the inductive load, what is the voltage we have lost? We have lost this voltage, right? We have lost this voltage. Am I correct or not? What is the voltage we have lost? How? Okay, if we suppose we are applying the alpha at 0, alpha equal to 0, right? Then VD 0, just a moment. VD 0 will be your 0.9 Vs, right? And VD alpha, because of the inductor, we are getting 0.9 Vs cosine of alpha. So what is the voltage then we have lost? That is your VDO minus VD alpha. That will be your 0.9 Vs 1 minus cosine of alpha. If alpha equal to 0, then how much voltage will lose?
No voltage is lost, sir.
No voltage is lost.
So VD 0.9 Vs or 0.45 Vs?
This is a full wave rectifier. So for the full wave rectifier, you will get this one. Then what will be your average value? If we apply the firing pulse here, for the full wave rectifier, what will be the average value?
Yes, sir, 0.9 Vs, but then in the equation it is coming 0.45 Vs.
Equation.
The root 2 Vs by pi cos alpha.
Okay, VD alpha, how much we get? 0.9 Vs cosine of alpha. If alpha equal to 0, it will 0.9 Vs. What do you say? I don't understand. Please repeat again. What do you say?
Sir, the equation it was VD alpha is equal to root 2 by pi Vs cos alpha. So root 2 by pi is 0.45.
It's 2 times 50 by 5.
So it should be 2 times.
Where I have written like 1 by pi, then it is alpha to pi plus alpha, right? Then root 2 Vs sine of omega t, d of omega t. This is your VD alpha, right? Then it should be 2, oh, okay, this 2 is omitting. Yeah, it will be like this, cosine of alpha, yeah. You correct it. But I omitted this 2, right? That time?
Yes, sir. I think that's it.
Okay. Yeah, because you look here, if you complete the integration, let us, this is your fundamental things. Vd alpha will be 1 by pi, then pi plus alpha, then root 2 Vs sine of omega t, d of omega t. Then it will be your minus root 2 Vs, other than minus cosine of alpha. So pi plus alpha, then alpha. Then it will come as 2 root 2 Vs by pi cosine of alpha. You can check at your room. Yeah, it is okay. Equation number 6.6 of your book. You can check. Okay. So it will be 0.9 Vs.
Okay, sir.
So the voltage we have lost, that will be your 0.9 Vs cosine of alpha. So you correct that thing. If I write down root 2 Vs alpha, it should be 2 multiplied by root 2 Vs cosine of alpha. Okay.
Yes, sir.
Now we want to plot the Vd versus alpha. So now Vd will be, or Vd alpha will be 2 root 2 Vs cosine of alpha, and Vd 0 will be 2 root 2 by pi cosine of alpha. Then the Vd alpha by Vdo, which will be cosine of alpha. Now if we plot that, this will be your alpha, and if we plot Vd by Vdo has been replaced by Vd alpha has been replaced by Vd here in your figure number 6.7 of your book. So they write down Vd by Vdo. So this one is replaced by Vd. Okay. So it is just a cosine alpha. So if you plot it, it is nothing but the cosine like this thing. So what will be this one? VC sir has found. Yes. Right. Okay, so you understand, we are plotting the cosine alpha, which is nothing but the cosine alpha. So what should be this value alpha?
Pi.
And this will be 1, and this will be also minus 1, and this should be a pi, right? So the control parameter, controlling range of alpha should be 0 to pi. You understand it or not? If you want to get negative value, then you have to operate your firing pulse between your yes, between your pi by 2 to pi, right? You understand what I say? If your alpha is greater than pi by 2 and less than pi, then your output voltage will be negative. This will be negative. This will be negative. Then you will get that inverse. Rectifier mode, and this is your inverter. Can you hear the sound of the sky?
Yes, sir.
Understand? I'm sometimes people operate your Wi-Fi, then you know what happens? The router it goes. Anyway, let us see how long we can proceed. Now, the ratio of the current will be IS. So that will be your right. So this is your alpha. This is your pi plus alpha. And this is your twice pi plus alpha. Suppose this is your pi. Did you plot correctly? This is your VS. This is your IS. So IS is sinusoidal or non-sinusoidal? IS is sinusoidal or rectangular?
Rectangular.
Okay. So if I go to the Fourier series analysis, you will get 2IS1 sine of omega t minus alpha plus root 2 IS3, because your even harmonics will not be there, right? Because it is symmetrical with x-axis. So 3 omega t minus alpha, then root 2 IS5 sine of let me turn off the router and use the mobile phone. Let me go to the mobile phone. Okay, just wait. Hotspot. So can you hear me?
Yes, sir.
Clear?
Yes, sir.
Okay, so I have back to the mobile phone. Okay. Up the so look here, we have that this is the fundamental, so the frequency, the fundamental frequency, this is the third harmonics, this is the fifth harmonic. If you cannot listen to me, please tell me, right? Can you listen to me?
Yes, sir. It's
Okay.
clear.
Okay, so yeah, in our diode rectifier, we have already seen that this is your ID. So the RMS value of the fundamental component we have found. Can you remember what is the value we got? Hello? Hello? 0.9 ID. Can you remember that? You forget everything. So the fundamental, if you have that rectangular type wave and if the what is that? And the peak value is ID, then your fundamental component will have that RMS value will be 0.9 ID. We have already proved in our diode rectifier case. Anybody can remember, please? Can you remember this? Nobody. So you can go back and see the video, or also you can see the class notes. Okay, so and also the other component will be IS1 by H. Did I do this kind of thing in the 5th chapter, chapter 5? Hello?
I think so, sir.
Yes, sir.
Yeah. Yes. So this is your okay. Your 6.12, 1, 2, and 6.13 of your book. So we can find out the other component as, say, third harmonics will be IS1 by 3. Then 5th harmonics will be. These are the, of course, RMS value. Okay, these are all RMS. IS3 by 5. This way we can find out the other component. Okay. Now, if we plot the this part, look here, then it will look like this. So there is a lagging, right? Voltage and IS1. This will be IS1. So there is a lagging. IS1 lagged by an angle. What is this angle? What is the peak? What is this peak value? This peak value will be due to IS1, right? You understand it or not?
Yes, sir.
Peak value will be from here, from the equation. We see that it is due to IS1. Okay, and we know the IS1. If you know, I say ID equal to 10, then IS1 will be 9, and 9 multiplied by root 2 will be your peak value of your fundamental component. Fundamental component is lagging with your here's voltage by an angle. Which angle?
Alpha.
Alpha.
Alpha. Alpha is the firing angle, and then your displacement angle. If you remember that, did I define displacement angle? Displacement angle is defined between the angle between the sinusoidal input and also the fundamental component of the current. So that is your alpha, so it is alpha. So displacement angle phi will be your alpha. Okay, now figure 6.8. Okay, let me go back to the book. I'm sharing the book now, okay? These are the things we have already covered. Covered. Resistance covered. We are here. We are here. So now they want to plot the with respect to harmonics. Harmonics is the H, and we know that SH will be IS1 multiplied by divided by H. So if we write down ISH by IS1, that will be 1 by H, right? So when H is equal to 1, then you will get 1 here. If H is equal to 1, then this one will be 1, that has been plotted. If H is equal to 3, then it is 1 by 3, 1 by 5. If it is 7, 1 by 7, 1 by 9, 1 by 11, this way. So you see that it is dying out, right? Higher harmonics is dying out. So basically, if you want to use any filter, we have to filter out the third harmonic and fifth harmonic. And then you will get almost sinusoidal component of your input current. Input current, if you filter out this third harmonic and this fifth harmonic, so rather you will get this one, you will get almost the sinusoidal. You understand what I want to say?
Yes, sir.
Hello. Okay. Now, here, what are all those things? Try to look at the things, then that will be easier for you. Okay, we'll come back, probably that will be easier for you. We'll come back later. This figure. Let us do some of the things. First of all, okay, there. Okay, let us see this one. So, if you remember, in the diode case, we have already told that thing. If it is IS, and if it is the peak value, what will be the RMS value of the IS? You forgot everything. How come you can forget? I don't understand. So if you have a rectangular wave and it has a peak value, what will be the RMS value of this one? You square it, and then you take the average value and then divide it by the time period. It should be
ID, sir.
peak value. Okay. And total harmonic distortion, that has been already defined by this equation. So IS equal to, say you put ID and this is your 0.9 ID, and even ID is 0.9 ID square divided by 0.9 ID, and you will get 48.43%. What does it mean by 48.43%? What does it mean by 48.43%? For total harmonic distortion is coming as 48.43%. What is the meaning of it?
So the other harmonics other than the first harmonic is causing a distortion of this one.
Yes, if we have only the fundamental component, that means if this one is the sinusoidal, then this IS will be your IS1 and then your total harmonic distortion will be 0. So if the total harmonic distortion is higher, that means you have contaminated your input current. You understand it? And it is almost 50% you have contaminated from the fundamental value. You understand it? What I say?
Yes, sir.
So if your input current is fully sinusoidal, then total harmonic would have come as 0, right? But since it is not sinusoidal, rather than the rectangular because of the highly inductive load, so we have contaminated the input current. But that is not acceptable. What is the acceptable limit? I have already told you. 6%. 6%, right? Now 6.1.3. So power factor, reactive volt ampere. So deflection power factor, we have already know that is your cosine of phi, right? We have defined it, and this phi is alpha, and we got this one. Then power factor will be defined by IS1 by IS. So IS1 is equal to 0.9 ID, and IS equal to ID. So ID cancel, and this is already cosine of alpha. So we are getting power factor will be 0.9 cosine alpha. You got my point? If you remember for the diode rectifier, what was the power factor we got? Uncontrolled rectifier, what is the input power factor we got? 0.9. Can you remember? Because alpha equal to 0. Right or wrong? So you forgot everything. This is your B. So it is pi. So we got this one, and then alpha was 0, and then we got input power factor for the diode rectifier. Diode rectifier was 0.9, and here 0.9 cosine of alpha. Now, if the cosine alpha equal to say alpha equal to say 90 degree, what will be your power factor?
0.
0. So is it good or bad? Extremely bad. We want the input power factor as close as 1. You understand it or not?
Yes, sir.
Okay. Now, next equation, if you see that, this one is that from the AC side, we are talking about the AC side. Suppose this is your rectifier, control, rectifier. This is your AC side, and this is your say VD alpha. So we have applied the. You see that our input voltage is this one, and input current will be like this. And this point is alpha. If you remember this, and this is your IS1, right? So when you write down the equation, you have to write down the not the rectangular with the current with the rectangular, rather than you have to write the sinusoidal. So sinusoidal is this is your IS1. Write down VS is sinusoidal, IS1 is the RMS value of the sinusoidal, and cosine alpha is the power factor. So this is your input power. Output power will be what? What will be the output voltage VD alpha? Tell me quickly. 0.9 VS, then
Cos alpha.
cosine alpha. Good. So, and then you have to, if you write down the output power, you have to multiply it by ID, because this is the constant, and we are getting this. So now if you equate P in equal to P out, PD, look here, VS IS1 cosine of alpha, that will be your 0.9 VS ID cosine of alpha. Cancel. Then IS1 is equal to 0.9 ID also. What's going on? Okay, forget about it. Will not say anything. I always make confusion with this one. Okay, just hold it later. So this will be your actual part. P is the actual part, and this is the apparent part with the sign thing is the apparent part. And then what will be the, sorry, this will be the reactive part. Then what will be the your apparent part? Yes. Yes, this one will be VS1 multiplied VS multiplied by IS1. That will be P multiplied by Q1. You know this equation, right, from the power system. Do you know it or not?
Yes.
Yes, sir.
So that is your apparent power. And this will be your VSIS. S will be this one. But this IS will be your capital ID, right? And that has been plotted in figure 6.8. See that I told you. I'll come back and let us first see the equation. Okay. So they have plotted here. First one, this is S, VSIS, VSIS. This is the constant value. This will be your VSIS. So VS is constant, IS is constant. It is of course equal to your ID. This is the RMS value, and then with just to there is no function of alpha here, no. So it is a constant, right? And IS1 is equal to VS IS1 is your 0.9 ID, right? And then this will be your this one is equal to 0.1 difference. So you are getting also this one. And what will be the peak value? Okay. If you now plot P and Q, so P will be if you go back to the equation, P will be what? Tell me please very quickly. IS1 cosine of alpha, right? Hello.
Yes, sir.
So this is the cosine. This is your cosine wave, and this is your sine wave. Q1 is the sine wave. Q1 equal to VS IS1 sine of alpha. So with respect to alpha, I hope you have understood this one. These are the very easy things. Yes or not? Hello.
Yes, sir.
Nadim, are you around today? Nadim is not here today. So, what is the time?
9:40.
9:40. So should we start the effect of LS today, or we'll defer it for the next class? And with that one, that will be the syllabus of the midterm. I think we'll do that thing, right? With the LS, we shall solve this problem. And this one in the next class. And these practical things we will cover inshallah in the next class. And until this will be done. Okay. Until this will be the syllabus of the midterm. So if you want, I can continue, or I can stop today. What do you want?
I think this is enough for sir today.
Okay. Yeah, because I actually go very fast today, right? Yes or not?
No, sir, you are okay.